I don't know. I kind of find the Miss Ashton side of it all right.
Yeah.
It's just your side, like all the waves and stuff. But like, I don't have any questions. It's just, you know, when you start on a topic and you don't really get it, but you just try.
How are you coping with things like path difference, etc.? Do you understand that?
I think I get them. I just get confused between path difference and phase difference. But is phase difference like where where a specific like particle is in its cycle, and then path difference is like how much of the wavelength it is across?
Yeah. I'll try and turn around and see it. So we've had this last week, and I'm not surprised at all. This keeps coming up, this question. I'm trying to visualize in the right place now. Very annoying. My screen's back to front. I don't know how you change that. I'll have to work on that one. First of all, if you take a wave, okay, and this is like, and Jacob was asking about this last week as well. If you take a wave, for example, Macy, and do a snapshot, you've got all your particles are basically going up and down, but there are something called a different part of their phase. Now, what we say is here is going to be a naught, and here's going to be your 360, okay? And what we do then is we map this, is exactly the same, I'm going to get them right on the screen here, is something going around in a circle, okay? So something going around the circle here, we say here's 0 degrees. Here, as it goes around here, is going to be 180. As it goes around there, here's going to be your 270. There's going to be your 90. And then, space here, there's going to be your 360 at the top again.
Yeah, I think I get that.
So this is basically taking a snapshot of a wave at a certain time, okay? It's at whatever it is. So it's like, this could be, it's a bit like angle against time here. You're freezing it at a certain time, okay? Yeah. So we then say they are all in a different part of their phase. So rather than using degrees, and you'll see why it's come more out in the mathematics, we actually use this, well, I think it's 360 there. We're going to get a different color pen here, why not? We then say that is going to be 2 pi, because we do it in radians. Therefore, this point here, which is 180 degrees, we say is pi. Here's going to be 90 degrees, which is going to be your pi over 2. And this is going to be your 270 degrees, which is going to be 3 pi over 2. Okay?
Why is 180 pi, like when a full circle's like pi?
Yeah, they did it. It's all come back. Do you know, have you done work and when you've done angles and radian and you've got arcs like this? You know, you've got the circumference of the whole of a circle. We say it's ended up being 2 pi r.
Yeah.
That's where this 2 pi comes from, because it all comes with the fact, if you're measuring the angle in radians, is all to do with the ratio of this bit here compared to the radius.
Okay. All right.
That's how they did. That's how this. If you take if you take your whole of your angle going round divided by r, you get 2 pi, and it's basically the way to define the radians came out. So don't worry too much about it. It's all about using the ratio of the arc compared to the radius, and this is where the pi's came from. So you'd have to just accept that end up being pi is going to be 180 degrees. But what it allows us to do, it tells us then the phase difference from these two particles, they are going to be 90 degrees out of phase. In other words, if one particle is going to be here, the other particle is this part here going to be 90. This one down here, it's at the bottom, is going to be 180. Okay? Because if I take time forward, this next particle is going to go up slightly because this part of the wave is going to come across. Yes. If I then take this particle here, as the wave goes across this way, it's going to go down, start going down, because they're going to be at different part of their phase, if that makes sense.
Okay. So how do you know whether the particle, whether, you know, pi and 2 pi and 3 pi and so on, how do you know whether the particle is going to move up or down in the next second or two?
Then you basically go all the way across to your 2 pi and you just keep going. And then you can repeat them all over again. It doesn't really matter.
I mean, like, so at pi, you said that it moves up after like another second. How do you know that?
Because you got to imagine this wave here.
Yeah.
Wave is going that way with time, isn't it?
Yeah.
So if you've got this part of the wave is going to go that way. Therefore, it should be over there, which means that particle must go down.
Oh, okay.
Particle must go up and down like this, as for the wave to go across like this to be a traveling wave. Does that make sense?
Yeah.
Yeah.
Okay. So basically, the wave is changing with time, and this time aspect is showing how. Because if you look at a wave, it goes up and down with time. I can get on a simulation in a minute; it might help. I think Jacob quite like that last week. I showed him, and I'll go back in a second with that one. Now, the other way of looking at it, when it comes to path difference, is then you're now looking at a wave, and this is like drawing a wave now, and therefore we say this is going to be a complete wavelength. I'll get back up again of the wave going across here. Now here now. That's going to be half a wavelength. This then goes over here is going to be a 0. And what you got then is your quarter a wavelength here. And then this point here, I'm trying to get my board up a little bit. Very small screen here. And this kind of point here is going to be 3 pi over 4. Now, all this is doing now, Macy, okay, is rather than looking at the one particle, how it changes with time going up and down, going through here, this phase going around, look at the phase in between them, is now looking at the length of the wave. Are you looking at a whole wave going across here? So you can, and I sometimes superimpose these on top each other, is that then, and I'll use a different color here, I can call that one wavelength. I then go over here, say that's going to be half a wavelength. Then I say that's going to be 3/4 of the wavelength. And then this is going to be quarter of the wavelength is going to be your 90 degrees. Okay. So that is looking at the wave itself, but then that is looking how it changes with time. This is looking at it one instant, bang, and time can't change now. That's looking at the wave. So the time is fixed. Here, this is changing with time. Okay, because it's going around and round and round in my little circle. We use that because it shows us when we get to Young Slit's interference patterns. Now, when you've done, and I think you've started to see the video of Young Slits now, haven't you?
Yeah.
Now, this comes out, and he got numerous videos about this. I just find it quite remarkable. He did this with a candle, you know, incredible. Because there was a mass debate, is like it was going to be waves or a particle. And it basically created more of a can of worms, you ask me, because it actually showed that light should be a wave, but we now know, and we have done a little bit before, that light waves can be particle and a wave at the same time, which is really weird and confusing. But what you've got is you've got your S1 and your S2. Okay? Now, these then waves travel out, and then if you've got a center point here, the two waves travel out like this, traveling out from S1 and the S2. Now, the work you've done, and we show you the videos of this, we then know we get a bright one here, then it's going to be dark, bright, dark, all the way out going like this.
Why is that, sir?
Now, the reason why is because then, and this is where looking at the path difference, and I'm going out a different color pen now here. When this wave travels out from S2, it goes up and down, up and down, up and down, up and down, up and down. This one, very, very cunning here, different color pens. Whoop. Up and down, up and down, up and down, up and down, up and down. Okay. They then meet here, but what we say then, they meet in phase. What I mean by that is, if I look at my circle going up and down again, okay, let's say the phase difference is going to be 0 degrees or 0 pi. Both of them must be up this point here and the cycle going round and round and round like this. In other words, at that point there, one wave, the purple wave, must be going up. And I get back to my red pen, which I seem to have lost. Oh no, it's here. The red pen also must be up. Therefore, if they meet at the same point here, at the top, they're in phase. Therefore, we say you've got constructive interference, because two waves add together like this. they then make our super wave, which has double the amplitude. If that had A and that had A, it means this one is going to be 2A. Okay? So we say the waves meet in phase. And the reason why they must meet in phase is because if this is the halfway point, if this one goes up and down, let's say for argument's sake, it goes up and down 4 wavelengths. Well, the purple one, carrying on my color theme here, because it's going the same distance, won't it also go up and down 4 wavelengths? Has to be. Therefore, we say then the path difference is going to be 0 wavelengths because they're meeting in phase. Therefore, we got constructive interference. Now, if this point just here, this way this diagram can get a little bit messy, but we'll see how we get on. Now, this one, S1's gone up and down like this. And then you've got the next one going here was going to be S2, which also goes up and down with this. Can you see now S1 has got to travel further than S2? Has to. Yeah. Now, in that case then, and I'm making numbers up here, I'm going to say S2 is going to travel, I'm going to say 6 wavelengths. Okay. Then S1, I'm going to say is so that one, S2 goes 6 wavelengths. I'm going to say S1, let's say it's gone 8 wavelengths. And the reason why it's gone 8 wavelengths is because it's traveled further. We then say, what's the path difference? 2 pi. But it's a whole wavelength difference. Therefore, they still must be in phase because they will both, this one of them has gone around 1, 2, 3, 4, 6 times, and one of them's gone around 8 times. Won't they both be at the top of the cycle? Therefore, say constructive interference is when you got a 0 wavelength or a whole number of wavelengths out. Now, the tricky one comes in, this one, and I'll do it over here. The tricky one is that point just there. Now, to get it dark, what must happen then? One of the waves must reach there at the top, and one must be at the bottom. In other words, for you get deconstructive interference. So one wave's at the top, one wave is going down. Yes? Can you see the phase difference is going to be 180 degrees? Because one wave top and one wave's down. Now, in that case then is, and this is where it will get a bit messy, my pens, but we'll see how we get on. S1 goes up and down like this, okay? S2 goes up and down like that. Now, to get deconstructive interference, I'm going to say S2 is going to travel, say, example, as an argument's sake, 6 wavelengths, okay? I'm then going to say S1 is gone 4.5 wavelengths. What is the path difference? Well, the path difference going between the two there, isn't it going to be 1.5 waves, correct?
Yeah.
Can you see now we get a deconstructive interference? Well, it's going to be deconstructive point here if you've got an extra half a wavelength because there must be 180 degrees out of phase. And that's why you can do it 2 different ways of the path difference being in degrees, or you can do it in path difference and lambda. Does that make sense?
Mm-hmm.
And this was, sorry, I'll come back to Joe what I was saying, this is why Young's realized when he got the interference pattern, they must be traveling at ways the only way they could explain it. But he had mega problems doing it. I mean, I will do it with the laser and you'll see a dark, bright. And I've got more videos appearing showing interference pattern. Sorry, question, is that Jacob or Paul? Not sure.
It was me. I was just wondering, what happens if it's like not a half? Are they always going to give it you where they're like totally going to destructively interfere? Then
what happens then, Jacob? You get basically a mixture in between. You in between these fringe patterns, yes?
Yeah.
Got bright, dark, and you've got a sort of merging in between because you may get phase difference. I think to show you perfectly, and
do an example of that.
Yeah. This is where. Yeah, I'll show you. This is where. Oh God, that's my screen. Ooh. Not my screen. I thought there was a way of showing desktop here. That's a whiteboard. That's Mel. I don't want that. I wanted to show you my computer screen. And I thought I could do this on here. Oh.
You can share screen, can't you?
Yeah, that's what I thought. Let's share screen.
Alt.
That's seeing the video, isn't it? That's going here. I'm sure there's a way to do it. There we go. Make that bigger. There's a way to show the screen because this shows you the. Right. You can see my screen now, can't you?
Yeah.
Ooh.
Right. Yeah. Right. You still there, everybody?
Yeah.
And I'm a bit terrified of pressing the wrong button here and everything go pear-shaped. Now, what I do, and I've tried to do this in the videos, and it's much better in the lab doing with you, and that's why I wanted to do a little tutorial as well. This software here is just absolutely fantastic, and it really shows it to you when I get to the right one. I'm on the wrong chapter now. I wanted to go to optics, not waves. And this shows you exactly it happening in real, well, it's a computer simulation of it. Get Young's there, and somewhere here I've got Young slits. Here we go. So hopefully it's going to work. Come on, a lot better. So what you've got here, I have to move you around, this is the interference pattern when it comes out going here, and I've got, sorry, you're right in the way of my, here we go, right. The interference pattern itself, coming out here, is this is what this that shows it nicely. So what you've got here, there's your source 1 and there's your source 2. Okay. Now these are the wavefronts going out. So I'm going to say that's top of the wave, top of the wave, top of the wave, top of the wave for S1. Okay. Then for this one, S2, whatever you want to call it, there's going to be top of the wave, top of the wave, top of the wave. Can you see as the waves go through, you've got a top of the wave here and top of the wave there. So what we then say, we've then got reinforcement here, reinforcement here, reinforcement there and there. And you can take the other one going out like this and basically go on the top of the waves. But this one, if I go to this point here, that's traveled 1, 2 wavelengths. You see this one has gone 1, 2, 3. Therefore, that's got 3 lambda, that's got 2 lambda, half difference is going to be a lambda. Can everybody see that?
Yeah.
Yeah? Now, for your cancellation, which is the hard one, so I'll show you the video in a second, it's going to be here. So your cancellation is going to be right in between where you're going to start, we'll go through it, and that point is going to be here. Now, why it's here is because now this one's gone 1, 2, 3 and a half. Can you see that? This one's gone out 1, 2, 3. 3 and 3 and a half. Half difference is going to be half pi. And that's why you get your cancellation happening out. So what you can start seeing, I can do ask about it, how you get interference pattern forming. And I think you've seen it on the videos. What we do is a ripple tank is there's your source 1 and there's your source 2. Can you see where you got the wave coming out? And you got like a, well, it's like a blur here and a here. You can start seeing a fringe pattern coming out of each of them coming through. But that's demonstration using water waves, and we can do it with lasers, and it works out nicely. And that's basically what Young's did. And here's showing you here. Here's where you got source 1, source 2. There's going to be where your constructive is. There's your deconstructive, constructive, deconstructive going across, and that's, we call this the fringe pattern. And I think Mr. Mumba's video, he did, he then showed you that this what happens that you eventually see, that's a green light where you got the interference pattern happening. And I think you got the video out this week, didn't we? Showing the fringe pattern like this. Is that correct?
Yeah.
Yeah.
Yeah. It's a quite difficult concept, but when, and then these are showing the path difference, they go out showing how you got the interference pattern happening. A lot of the time what I do is I do it using path difference, which I find a lot easier to use. It really explains it. Is everybody happy with that? Paul, does that answer your question?
Yeah, that explains it.
Yeah, but you can do it in microwaves, Paul. But bizarrely, and it's what they've worked on this, we can do it microwaves, sound waves. They're trying to do it with big TV screens where you can have a big TV screen, have multiple pictures. And what, well, so say example, you've got whole family sat on the sofa looking at a big TV like this. Oh, I need to share my screen back now, don't I? Ooh. That's As you start talking, you forget we're not sharing. How do I get back to my video? There's screen, whiteboard. Oh God, that's a very good question. That then.
I think you just stop sharing the screen and it'll come back.
Oh, stop share. There you go. Thanks, Paul. You've got a TV screen like this.
Yeah.
What they can do is say they got 4 different pictures going like that, and everybody's staring at it. Well, what they can do is everybody can only hear what the sound from one screen by using interference patterns. So at certain positions, the sound waves are cancel out, and they've tried to do that to varying degrees of success. But interference, it's a beautiful concept, and it does happen. But it was conclusive theory to Young that light had to be a wave property. Then obviously it all fell apart because they realized they could use the wave property to explain the photoelectric effect, which we did earlier in the year.